Hello, welcome to today's lecture, 5.5. So today we're going to be talking about a bunch of other integration techniques. So far we've done U substitution and integration by parts. Those are two of our most commonly used integration techniques. Today we're also going to look at partial fractions, which is probably number 3, as well as trig integrals, integrals involving sines and cosines, as well as kind of a method of choosing a technique, having an idea of what's going to work. The first section here is I'm calling basic integration techniques, and that's just kind of what the name the book uses. Doesn't mean they're easy necessarily. It's just kind of a couple of algebra tricks that you can try that are just algebraic, that don't need like really some special like extra rules. So we'll see what that means, but basically we want to expand our library of integration techniques and be able to integrate all sorts of things. So let's start off with this first section. So there's basically just going to be kind of a grab bag of a couple of different sort of algebra tricks that come up now and then, and we'll just see a couple of examples. So I'd say first of all, I'm calling this one splitting the fraction. So just remember, whenever you have an integral of like a fraction here, it looks a little bit scary, but remember how fractions work. We can always split the numerator into a sum of things with the denominator, right? So this is the same thing as the integral x squared over x cubed plus 2x over x cubed plus 1 over x cubed. So I can always split the fraction up like that. It's very often a good idea to do that, especially if each of these individually are things that you have an easier time doing the integral of. Pretty often you're going to simplify these. So like here, x squared over x cubed, that's 2x's on the top, 3x's on the bottom. 2 of them will cancel. And I'm going to go ahead and write each of these as a separate integral. Because remember, one of our integral rules is we can split up the sum. That's the main reason to split up the fraction, is because I can split the integral over the sum as well. For the middle one, I'm going to have 2x over x cubed, so that's 2 over x squared. And for the last one, I'll just keep it there. So each of these is an integral that you can do. So you might have to remember this first one is ln. The second one, we can pull the 2 out, and I like to write this as x to the minus 2, so that I'm going to be able to use my power rule. Remember, 2 in the bottom is the same as minus 2 on the top. This is x to the minus 3. So we'll still have log x, and then here I got to use my power rule, so x to the minus 2 goes to x to the minus 1. I do plus 1, right? And then divide by the new power. And then the last one is going to be x plus 1, so x to the minus 2 over minus 2. And I'll throw in the plus c. So yeah, so just don't forget, when you have something that looks like this, a sort of big algebra chunk on the top, and maybe something simpler on the bottom, you can always split it like this. A theme that we're going to be thinking about today is, what do you do when you have a random rational function? So rational function means I have some polynomial on the top and some polynomial on the bottom. So for example, we could have like the one we just had, a rational function. There's a polynomial on the top, polynomial on the bottom. But you could have something like this. That's some random integral. You could have something like this. That's some random integral. So it's pretty common to have some polynomial on the top, some polynomial on the bottom, quadratics, cubics. And depending on the details of how that's arranged, we're going to see that sometimes one technique is better than another technique. So as we do these examples, I'll point out where we're seeing rational functions and what the structure of the integrand has to do with what technique was good. So like on this problem, the structure that was helpful was that there was a sum in the numerator, right? I had 3 things added together, and only one thing in the denominator. So it was possible to split it up like this. If you have something like this or like this, there's not a single thing in the bottom. There's a sum of things in the bottom. So it seems like it'd be a lot harder to split it up like that. But yeah, if there's only one thing, you can definitely split it up like that. So it's kind of a simple version of polynomial divided by polynomial. Okay, so the next one is also along those lines. So here we have a polynomial divided by a polynomial, but it's a sum on the bottom. It's not just a single thing, so we can't split it up. So it turns out, this is a little bit annoying of a detour, but it turns out that maybe the easiest way to do these integrals is to remember something that we may or may not have done at some point, maybe in high school, not just long division, polynomial long division. So it's doing long division when you have polynomials. So notice here that the polynomial on the top is degree 2. So degree just means what's the highest power. The highest power is 2, x squared. And the bottom is degree 1. The highest power is, this is secretly x to the 1 plus 4. Whenever you have a degree something polynomial on the top, and whenever you have the polynomial on the top is a higher degree than the polynomial on the bottom, that means you can try long division. It's going to maybe be possible. And we'll see it turns out that doing that long division makes it easier to integrate. Basically, in the end, I'm going to have this like sort of split up into something plus something plus something, and it'll be easier to integrate each of those somethings. So it seems a little random, but we have to kind of remember how polynomial long division works. We won't be doing this all the time, but it's a good thing to know how to do, and it's not that bad. So first, let's maybe remember, just off to the side here really quick, how like regular long division works. So let's say I was doing 125 divided by 5. How do I do this, right? I think, okay, does 5 go into 12? It goes in twice, right? So I put a 2 here. And then I take this 2, multiply it by the 5. So I get something down here. I subtract. I have a 0, or I have a 2. And then I have the 5. I kind of bring this 5 down. So we have this structure, right? And then we repeat it. I now say, okay, does 5 go into 25? It goes in 5 times. And then I do 5 times 5 again. Double check that you get 0. And indeed, we get 0, so we get no remainder. Real quick, before we go on to the polynomials, I just want to say, if we were doing like 126 divided by 5, we'd get the same kind of thing going on, right? We get 2 and then 6. And then I go 5 into 26, and it's still 5. But now I have 25 down here. I have 1 left over. And probably when you learn this, you probably learn to write like remainder 1 right here, right? However, notice that we could write this as maybe plus 1/5. So let's justify that for a second. What happens if I do 5? Right, the whole point of long division is to figure out 5 times what makes 126. So if I do 5 times 25 plus a fifth, I should get 126 back. So 5 times 25 is 125. We saw that earlier. And then I have to add on 5 times a fifth. Oh, that's going to be 1, right? 1/5 is the thing that when I have 5 copies of it, I get 1. So 5 times that 1/5 is 1. So altogether we have 126 when I do 5 times this result here. So although we usually write like remainder 1, that secretly means, or you could also think of that as plus a fractional bit, plus whatever this is here, this 1 left over, divided by the 5, divided by the thing on the left. So we're going to see that structure, this plus an extra fraction at the end, come up in the polynomial version. Okay, so let's look at these polynomials. So we just set up the division. pretty similar to how we do long division. Remember, here I did 125 divided by 5. So I do the big thing inside divided by the smaller thing outside. So we write it the same way with the polynomials. We put the big polynomial that we're going to divide in the inside, and we put the thing we're dividing it by sort of on the outside like that. Okay, so I'm just going to kind of run through how this works, and we will see how it goes. So the first thing is you ask yourself, okay, I look at this x, and I say, does this x go into the first term? Very similar to asking, does 5 go into the first stuff? Does x go into x squared? Yes. The question is, x times what makes x squared? Or I could imagine x squared divided by x makes what? In either case, the answer is x. So that's the thing that I write up here. So I basically divide the x squared by that leading term by the x. Just like I sort of divided the 12 by 5, and I got 2, right, knowing that there's going to be some leftovers. Okay. Now, just like I take 2 times 5 to get 10, I'm going to take x times this thing I'm dividing, and I'm going to write it right here. This is a little bit weird, this step, but you're going to be timesing the x on the entire leading term. On the entire term here. So onto the x and onto the 4. So x times x is x squared, and x times 4 is 4x. Because x plus 4, I get x squared plus 4x. Okay, so this is like my 10 here. I'm going to subtract it off. By design, the x squared and the x squared is always going to cancel and get 0. You should always get 0 right there. Just like these 1s will always cancel. Now I got to do the next part. I do 2x minus 4x. So that's negative 2x. And then lastly, I bring this down. It's a negative 1, so I bring negative 1 down. So it's a little weird if you haven't done it before. It looks like regular long division, but we're kind of doing it with polynomials. So let's do another step. We just repeat this process until we're done. So again, I look at my x, and now I look at the new leading thing that I'm under the division sign. So x goes into negative 2x. Again, same thing. How many times does x go into negative 2x? Otherwise known as, if I take negative 2x and divide it by x, what do I get? And the answer is negative 2. So now I take this negative 2, just the negative 2, and multiply it through this whole thing. So I'm going to get negative 2x minus 8. Right, I have negative 2 times 4 is minus 8. And it's a really good idea to put this thing you get in parentheses so that when you subtract it, you know where all the negative signs are. Okay, so now we just do our subtraction. Again, this first one will cancel. It's designed to. Negative 2 minus negative 2, that's nothing. And I'll have 1 minus negative 8, or sorry, negative 1 minus negative 8, so negative 1 plus 8, so that should be 7. Okay, and then our final step sort of would be, again, come back to this x and see, does it go into 7? But just like we ended up with this plus an extra fraction at the end, we're going to have that here. We're going to have plus the thing that remains, 7, that's like the remainder, but divided by x plus 4. So I tried to divide the x plus 4 into everything. It's kind of like I was able to divide it into the first stuff, but then it didn't go in cleanly, and there's this like fraction left over, this remainder. Okay, so just let's recap the process, right? I checked, does x go into x squared? It goes in x times, I multiply that x through to get x squared plus 4x. I subtract that, to end up with negative 2x. I bring the negative 1 down to get negative 2x minus 1. And then I start over. I check, does x go into negative 2x? It goes in negative 2 times. Then I multiply that negative 2 through to get negative 2x minus 8. Then I subtract that, and we end up with 7. And then as the final step, I write 7 divided by the original thing we're dividing by. So the point of all this is that we have like a real, we learned something about our polynomial, right? When we did the division, right, the whole point of the division was that 5 times 25 is 125. So we learned that x plus 4 times, blank equals x squared plus 2x minus 1. That was the question we were trying to answer. What could fit there? And we learned that the answer was this. So what that means is that I could double check that if I multiply this through, I really get on the right hand side. So like that's what the long division is doing. But also in the context of our original problem, we had this polynomial divided by x plus 4, which looks like this guy divided by that guy. The answer was what we got, x minus 2 plus 7 over x plus 4. And again, because I can split the integral over the different parts, integral of the first part minus integral of the second part plus the integral of the last part. The hope is that each of these parts is maybe easier than the original integral was. And in fact, in this case, we can do them, right? This first one, integral of x, that's just x squared over 2. The second one, the 2, is just going to become 2x. And then we still have to do this last one. So this is going to happen. Usually this last one that has like the extra division in it is often going to be like another little integral to do that might be tricky. But we've done most of the problem. We just have to think about how we would do this last part. So I think I'm going to let you try to fill out how you would do this last part. I will give you a hint to try u sub and see what you can do. U sub is going to work. Okay, so remember our theme today is when we have polynomial over polynomial. So we saw in the first problem that when the bottom polynomial was just a constant, was just a single term, we could just split it up, and that was not too bad. In this example, the degree, the top polynomial has a higher degree than the lower polynomial. So that means we can do division. If we had the bottom was the larger one, something like this, even though it looks pretty similar, it's like suddenly way different. Like this is a way harder problem, or we can't use long division on this one. So it really matters exactly what the degrees are. Okay, so if the top is larger, try long division. If the bottom is a single thing, just split it up. And I think maybe come back to that one in a second. Yeah, so just to go along with our theme, I just want to point out, so we'll come back here in just a minute, but I just want to point out that sometimes neither of those things happen, and or sometimes the polynomial long division doesn't work, and one of our other kind of cases is when the bottom one is larger. That's very often going to be a partial fractions. So we'll see how that works in just a minute. But before we do that, there's just a couple more sort of good algebra tricks to know that come up sometimes. So this trick I'm going to be calling completing the square. It's also making use of inverse trig integrals. So remember, and we may not have talked about this much yet, but if I'm going to integrate 1 over 1 plus u squared, that's arctan. I know that because that's a basic derivative that we learned from 251. You might remember that the derivative of arctan of x ends up being 1 over 1 plus x squared. So that's a nice basic derivative to have. It means that if I ever want to do the antiderivative of this 1 over 1 plus x squared, I know it's arctan. We had a similar looking one for arcsine. It's the integral 1 over root 1 minus u squared. So sometimes we have an integral which kind of doesn't look exactly like one of these, but maybe there's a hope that it could become one of those. So it turns out that when we have something that looks like this, like if you squint your eyes, this is like 1 over root polynomial. Maybe I could make it look like arcsine. If I'm able to do some algebra to turn it into this 1 over root 1 minus u thing, then I'll know that it's arcsine of whatever I have sitting there. So we'll see how that works. So our goal is going to be to do some algebra to make the bottom look more like this. So there's a couple of steps here which are slightly complicated, but let's take a look, and I promise it won't be that bad. Okay, so the first issue really is that we have like this big polynomial in here, right? It has 3 terms where the templates we're looking at, they only have a constant and a squared. So we really need to like work on this to have it be not 3 terms, have it just be something and a squared. What I would really like to do, what I would really like is if this inside was not written like this, but it was like maybe a number and then maybe like plus something squared. Right. If this number is not, like the number is 1 here, it turns out it'll be okay if the number is not 1. So as a preliminary step, I just want to get some number there. And there could be some chunk of algebra here, not necessarily just one variable. Like here it's just u squared. But it also turns out, probably because of a u sub, that if we have some sort of chunk of algebra here, as long as it's something squared, I'm going to be able to turn it into this. So I want a way to take this quadratic and turn it into like something plus something squared as like an in-between step. So it turns out there's a way to do that you may have learned before, called completing the square. So it's going to take a quadratic and turn it into this exact format, like a number plus something squared. So let's see what that looks like. So our polynomial is minus x squared minus 8x minus 7. So first of all, I'm just going to factor this 1 out. You're always allowed to do this, and just makes things, it's 8x, makes things a little bit easier. Now I can just focus on this polynomial and kind of think about the negative 1 later. So the idea behind completing the square is noticing that this quadratic is not a square quadratic. Right? What's a square quadratic? Imagine I had x plus 1 squared. You can check that when you multiply this out with FOIL, you get x squared plus 2x plus 1. So this polynomial, x squared plus 2x plus 1, it is a square. It is the square of this x plus 1. And there's lots of polynomials that are square polynomials. This one would be like 4x. And so if you ever have a polynomial that you can recognize as something squared, then you can rewrite it as something squared, which is nice. And you know, that's kind of what we're shooting for. Now, this x squared plus 8x plus 7, it's not a square polynomial, but I could try to like find the maybe like the closest square polynomial that I could think of. Notice here that when I did x plus 1 squared, I ended up with x squared plus 2x plus 1. Here when I did x plus 2 squared, x squared plus 4x plus 1. So I wonder, how could I end up with like 8x there, right? If I could get that to happen, that'd be pretty close to what we have. Maybe plus question mark? Well, probably x plus 4, right? Right, this 1 gave me the 2 x's. This 2 gave me the 4 x's. So you can check that when you FOIL this out, you get x squared plus 4x plus 4x, so plus 8x, and then plus 16. Okay, so our polynomial here is not a square, but it shares a lot, like it's almost the same thing as this x plus 4 squared. In fact, how far away is it from x plus 4 squared? Let's write this down. Maybe notice that x plus 4 squared is x squared plus 8x plus 16. So what? Let's make the right-hand side look exactly like our polynomial with the 7. What would I have to do to it? Well, the only thing I have to change is the 16, right? I just have to subtract something in order to hit the 7, right? So I think we're going to subtract 9. So let's take away 9 from both sides. Okay, so our polynomial was not a square, but it is this square, just minus 9. So it's just a little algebra manipulation to say, okay, it's not a square, but it's a square plus something or a square minus something. What's the closest square? And in fact, that's exactly what we're looking for here, because this negative 9 is going to be my number, and then the something squared is this x plus 4. Okay, so if we come back to our integral, I can replace all the stuff inside the square root with, yeah, so I was going to say negative 1. Remember, we pulled this negative 1 out. So since x squared plus 8x plus 7 is equal to the stuff on the right, that means that my original guy, this guy, is equal to that stuff on the right times negative 1. Which looks like 9 minus x plus 4 squared. Good algebra shortcut. If you ever have like something minus something, like a minus b, and then if I do negative 1 times the whole thing, that's just b minus a. So you can check that the negative 1 times a is minus a, negative 1 times negative b is positive b, and so they just kind of swap places. So that's what I did here, right? This x squared part and the 9 part swapped places. Okay, so our integral, square root of this negative x squared thing, same thing as square root of this thing. Okay, might not look like much, but we're actually like really close to making it look like this arc sine, right? How would I make it look more like that arc sine? Well, you'd kind of have to like squint your eyes a bit and say, well, what if this was a u? Then it'd be a u squared there. And we already know something where I can just replace stuff with u. That's u sub. There's just a little detail that we need to handle first, having to do with this 9. Because I really want to have a 1 there instead of a 9, right? If I have a 1 there, then I can directly use this formula. So this is a little weird, but just bear with me for a second. I want to think, what could I write here? Right, if I imagine like pulling a 9 out of everything in the bottom, that would be where my 1 is coming from, right? Because, you know, I'll have 1 minus something here, but when I distribute the 9 through, the 9 on the 1 gives me this 9. So I'm imagining pulling the 9 out. What would have to go in the second part? Well, it'd have to be whatever's sitting there, x plus 4 squared, but divided by 9, right? So this is just a little algebra move. Going from here to here, I like pulled 9 out of everything under the square root, leaving this 9 sort of in front, and then times this stuff. And you could double check that if you multiply this 9 through, you get the original back. Okay, I'm pretty happy with that for a couple reasons. Number one, I can actually pull this 9 out, Remember, one of my square root rules is that if I ever have square root of something times something, that's the same as square root of the first thing times square root of the second thing. So here I have square root of 9 times square root of all this stuff. And because of integral rules, I can pull the 1 over root 9 all the way out in front of the integral. Okay, cool. So now what we have really looks a lot like this arcsine thing. I just need to recognize somehow this piece as being a u somehow. Now, one way to think about that is just to force it to happen. Like, I want this to be u. So I could just write down u equals x plus 4 squared over 9. Or, sorry, u squared, right? I want this to be u squared because I want to have a u squared sitting in that spot. So you can do that. You can just force u squared to be this expression. Usually when we do a u sub, we phrase it as u equals. So I probably want to rewrite this as u equals. Well, that would look like taking the square root over here, right? One of our square root rules is that if you're square rooting a fraction, it's the same as square rooting the top and square rooting the bottom, right? So when I'm square rooting this, I have just x plus 4, don't need the parentheses, just x plus 4 in the top, and then 3 in the bottom, the square root of 9. You can double check that with this u squared gets me that on the top. I want to do it this way because when I do a u sub, I usually need the u equals so that then I can write du, right? Let's do that. Remember, this is, I can split the fraction up, x over 3 plus 4 over 3. So the constant that's on the x is really 1/3, and then I'll have dx. The 4/3 goes away. You might remember from when I did u sub that I like to solve for dx here, so we'll do 3 times du. Okay, so we can come back to our integral and plug all that in. So it's 1 over square root of 1 minus, this is u squared. That was the whole point. We forced it to be u squared. And then my dx turns into 3 du. So because of our integral rules, we can pull the 3 all the way out front. And now we're super happy because this is exactly arcsine of u. So we can write 3 over root 9 arcsine of u. And then the last step really is we just have to plug our u back in. So 3 over, by the way, root 9 is 3, right? So I can do 3 over 3. That's just 1. So it'll be arcsine of u is x plus 4 over 3. And I should probably have plus c here. Okay, so we have this kind of complicated looking integral, 1 over a root of a thing. We thought it looked a little bit like this arcsine guy. We did a little bit of annoying algebra to get it into a form where it was exactly that arcsine guy, maybe with this number up front. Then that's arcsine of u, and we plugged our u back in. So that is kind of a lot of work, but I did do it pretty slow and careful because you might not have seen this before. I will say that it's really good to be as fluent as possible with these algebra steps, like pulling the stuff out, working with the square roots. However, you can shortcut things a little bit. In this particular problem, we still had to complete the square no matter what, but you may have seen, if you're looking like in like an integral table or something, you may have seen like if it's square root of like a squared minus x squared, then that's 1 over a arcsine of x over a. So the logic of how to get from this side to this side is exactly this like pulling the 9 out and then going to arcsine thing that we just did. So I'll let you think through that if you're curious. And if you do have a situation, like this, it is okay just to directly jump to here if that's if that makes sense to you. But for us, we still had to get to this step in the first place. We still had to complete the square, so it's good to be able to know how to do that. Okay, so I will say that like it's good to be able to know to do this for like homework and stuff. On exam, I wouldn't ask you to do this whole complete the square thing because it's pretty tricky to get right, in a timed environment. But it's good to know that it exists and that it would be something like to know that it's something you would try. So I might have a question like, what technique would you want to use in this situation? And it'd be good to know when to try completing the square. Here we did it because I wanted this denominator to look more like one of these denominators. Okay, one more sort of algebra trick that happens sometimes. This is just kind of a minor thing. Don't worry too much about it. But I'll just show it because it happens every now and then. I'm calling it multiplying the top and bottom. So this is not even just a pure calculus thing. Just remember that if you have the square root of a fraction, you can square root the top and square root the bottom. That's the same thing. And a trick that is surprisingly useful is to take your fraction and multiply on the top and bottom by something. So you're always allowed to multiply on the top and bottom by the same thing, whatever your choice of same thing is, because that's like times by 1. And it's sometimes useful when you have like 1 plus x, 1 minus x kind of thing going on, because you will notice that like if we look at the denominator here, remember square rooting, like on the top I'll have square root of 1 minus x times square root of 1 minus x, so I can square root the first part times square root the second part. And on the bottom, same idea, square root of first part times square root times the second part. And then the main reason we're even considering this is because we have 1 plus x times 1 minus x. So you might remember, like an algebra rule, that if you ever have like a plus b times a minus b, you can check the foiling, right? A squared, and then minus ab plus ab minus b squared. Oh, and we get a squared minus b squared. So the ab's cancel out. So whenever you have this algebra show up, you can just change it to the first thing squared minus the second thing squared. And that's useful sometimes, because what it means is this bottom becomes so 1 squared minus x squared. And that looks familiar. That looks like square root of 1 minus x squared in the bottom. That looks like this arcsine that we just did. So sometimes there's secretly like an arcsine kind of thing hidden when you have some roots going on. Let's see what's happening in the numerator. This is square root of 1 minus x squared in the top, right? But the square root and the squared are going to cancel out. So you have 1 minus x. So it still looks like kind of a gross integral, but remember that I can always split a fraction. So I have 1 over root 1 minus x squared minus x over root 1 minus x squared. And in fact, because we're doing integrals, I can split this into 2 separate integrals, right? With a minus between them. So that's helpful if each of these integrals is one we can do. This one looks like arcsine that we just did a minute ago, arcsine of x. And then this one I will let you try this one. My hint is try u sub, try u equals 1 minus x squared and see what happens. Also using this lecture as an opportunity to suggest some u subs, and you can get a sense for when a u sub is going to be useful. Okay, cool. So it's just kind of a small trick, but it's helpful sometimes. Okay, so that's 5.4a. So we're going to start talking about partial fractions now. So this is one of our main, I would say, techniques, comparable to u sub or integration by parts. Probably a little less popular than those two, but it comes up pretty often, and it's slightly tricky. So let's talk about it. So the way I want to kind of frame this is, remember our theme today was polynomial divided by polynomial. We saw if the top polynomial was larger, we could do long division maybe. Here, the bottom polynomial is larger degree, so we're not going to be able to do long division. But it turns out there's a cool algebra trick we can do. So let's just start by noticing what happens if I combine these two fractions. So this is totally unmotivated. Where did I get these two fractions? We will see in a minute where I got these two fractions. But I want to remind you how adding fractions works and what's going to happen with these particular fractions. So remember that to combine these, I got to make the denominators the same. So this first fraction, I need to multiply the bottom by x minus 3 in order for it to match the other one. But the cost to that is multiplying the top. Like I'm allowed to multiply the bottom whatever I want as long as I multiply the top by the same thing. Same thing is going to happen on the right. I need to multiply this one by 2x plus 1 so that it matches denominators with the guy on the left. Now we can add these up. So they're going to be a single fraction with the same denominator, but the numerator is going to be the combined version. So for the first part, I have 1 times x minus 3, and then I have plus 2 times all this stuff, 2 times 2x plus 1. So 2 times 2x is 4x, plus 2 times 1, that's 4. And it'd be good to combine these, so we're going to get, I think, 5x, and then minus 1, all over this on the bottom, x minus 3, 2x plus 1. Okay, so now this 5x minus 1 thing looks familiar. It looks like this guy. Let's multiply out the bottom. So we get 5x minus 1 on the top, and on the bottom, so I multiply x times 2x is 2x squared minus 6x minus 3, and then plus 1 more x, right? So in the end, we get our familiar looking 2x squared minus 5x plus 3. Okay, so what happened here? Why did I do this? By doing some algebra, we showed that this sum of two fractions thing is in fact equal to this guy. Our goal was to do the integral of that guy. So the integral of that guy is the same thing as doing the integral of these two fractions. And those fractions are easier to integrate. These are both u subs. So you can try u sub on those. So the point is, right, here I just magically had two fractions who, when I combine them, I got the thing I'm trying to integrate. But if I started with, oh, here's a random thing I want to integrate, if it's possible to go backwards, figure out what those fractions were, the sum of two fractions, then I can just integrate the sum of those fractions. And hopefully those fractions are something that's easy to integrate. So that going backwards from the combined complicated polynomial divided by polynomial going backwards to a sum of several fractions is called, this whole method is called partial fractions. I'm not sure what the partial means exactly, but that's what it's called. Okay, so let's look at sort of the official technique. So the idea would be, well, what if we just guess or assume that our rational function, our polynomial divided by polynomial, just happens to be the sum of fractions, but with unknown numerators, right? So like, let's say, okay, I wish that this was two fractions. Well, yeah. I wish that this was two fractions, but I don't know what the fractions are. So I'm going to write A for whatever the top number is going to be, and I don't know what it is yet, and B for the top number. And then just because, we're going to put these here. So the denominator here, we saw from the previous algebra that it factors into 2x plus 1 times x minus 3. So what if, so that happened in our last example, right? What if this was always the case? What if I could just take my rational function and say, hey, let's factor the bottom into two factors. Let's just guess or assume that I could write this as something divided by the first factor plus something divided by the second factor. If that was true, then I could do some algebra to solve for what the a and b have to be, it turns out. So this is a little bit weird, like this is kind of a big leap. Oh, do I really know that every rational function could be written as the sum of two things? And then I just have to find what a and b are. And it turns out, yes, that actually works. You can just write down a over one factor plus b over another factor, and then do a little bit of algebra to figure out what a and b have to be. Let's see how we actually do that. So the idea is to focus on this thing being equal to this thing. Since they're equal, I can multiply both sides, and I want to actually multiply both sides by the entire denominator of the left side. So let's see what happens when we do that. If I multiply the left side by that entire denominator, then all that's left is the numerator. On the right hand side, I'm going to have a over 2x plus 1 times, I'm multiplying by this entire denominator. And then I have plus the b fraction times that entire denominator. Okay, the reason I want to do that, to multiply by this entire denominator, is that we're going to get some matching, right? A's denominator, like it got there because it was one of the factors. And so when I multiply by the denominator, it has both those factors in it, so by design, by default, those are always going to cancel. Same thing over here on the b, this x minus 3 and that x minus 3 are always going to cancel. So what you're left with is just a times x minus 3 and b times 2x plus 1. Okay, so some people just jump straight from here to here, and that's fine if that makes sense to you. You can think about it. But it's good to spell out that you get there by multiplying this denominator over. Okay, so the reason that we have a hope of figuring out what a and b are is that this left-hand side and the right-hand side have to be equal as functions. What I mean is that they have to be equal for any value of x. Right? If the left-hand side has an x in it, so it's a function, right? Its value depends on what x you plug in. The right-hand side is also a function. Its value depends on x. So if they're equal, that means they have to be equal no matter what x value you plug in. The graphs have to be equal. They have to match at every single x value. So what that means for us is that we uh, we can try any x that we want, and I get whatever falls out is an equation that has to be true. So for example, let's try x equals 3. So if we try x equals 3, then over here I get 15 minus 1 equals a times 3 minus 3. Ooh, that's a 0. Plus b times 6 plus 1. Okay, so this is why I chose 3, right? Because I wanted this a to go away. I saw this x minus 3, and then I said, let's try x equals 3, because I know that this term will go away. It will become 0. That's awesome, because the only variable that's left in my equation is b. I'm going to be able to solve for b. So let's keep going here. So this will be 14 on the left, simplifying. And on the right, we have 7 times b. And now I know what b is. B has to be 2. Very similarly, we can come back to our original equation and try a different x, which will get rid of the b term. So you got to think maybe what x could go here that would make that part 0. If you're not sure about that, you can always like write down the algebra. I want this to be 0. Algebra tells me what x has to be. So 2x is negative 1, x is negative 1/2. Okay, so x is negative 1/2 is the thing that will make that part 0. So let's do that. Let's try. So we'll come back to this. But continuing, we'll try x equals negative 1/2. So we get 5 times negative 1/2 minus 1, and that's equals to a times negative 1/2 minus 3. And then I don't even have to write the b part because I know that's going to be 0. Now again, we just have an a, so we just have to simplify a bit. This is negative 5/2. I'm going to write this as 2/2 to make that algebra a little bit easier. And then this is negative 1/2 minus, so 3 is 6/2, right? So this is negative 7/2, and this is a times negative 1 minus 6, negative 7/2. So a actually has to be 1 here. You can also use the calculator for that part, but it's good to be able to do that kind of fraction math by hand. Okay, so we figured out that a has to be 1 and b has to be 2, which means if we come all the way back to the top of our problem, that in fact we get, so a was 1 and b is 2, we get that our original rational function has to be equal to this. And you can check that if you combine those two fractions, you really get the original back. And in fact, we already checked that here, right? So we double checked that that worked. Okay, so again, the main method is just take your original rational function, write down that it's something plus something with the factors of the bottom, and solve for the a and b. There's a couple nuances here. Number one, how could we solve for a and b? It turns out there's actually 2 common ways to do it. I just showed you one way, and then we'll see the other way in a second. And then what exactly are my fractions going to look like? Like, is it always going to be, one thing divided by a factor plus another thing divided by a factor? And so we'll see that that depends a little bit on what the polynomials actually look like. In a lot of cases, it's just like this, though. So I mentioned that there's 2 ways to find a and b. So I'm going to call those 2 ways solving the system or plugging in numbers. So the one that we just did is plugging in numbers. That's this try x equals 3, try x equals that. That works just fine a lot of the time. It's pretty fast. a problem is that sometimes the way the equations are set up, like the only reason plugging in numbers was helpful is that by plugging in 3 we were able to kill this a term, and by plugging in -1/2 we could get rid of the b term. Sometimes because of how the numbers are, there's actually no single x that you can plug in which eliminates like all but one term. So it's good to know a more sort of general method to do it, and the solving the system method will always work. So let's see what that looks like. We're going to start from here. So you want to kind of get to this stage. So the idea here is going to be that right, the left and right side are still equal as functions, right? And in fact, they're not just equal as functions, they're equal as like polynomials, right? If I have like x squared plus x plus 1, and on the right side I write like a x squared plus x plus 1. If I claim that these two things are equal, then like if these are equal, then a is 1. Right? There's only one number that could possibly go here multiplying in front of the x squared. What makes something a polynomial is like how many terms does it have? Like does it have a 1, an x squared? And what the coefficients on those terms are. Is there a 2? Is there a 10? And I want you to think of those coefficients in front of each x power as like being a slot of like what number could go there. If two functions are polynomials and they're equal as polynomials, it means all those slots have to match. So if I have something that's, you know, even better, like, you know, x squared plus like b plus c x equals x squared plus 2x, for example, then because they're equal as polynomials, I would get to write down that this b plus c has to be equal to 2. So that's the kind of logic we're going to use over here. Let's multiply out the right hand side so that we can have it look more just like a polynomial on the right side. So we have ax minus 3a plus 2bx plus b. Now I want this right hand side to look like a polynomial, so let's put all the x stuff together and then all the not x stuff together. What's all the x stuff? It's a plus 2b. What's all the not x stuff? It's 1, or it's b, sorry, minus 3a. Okay, so now we can use that same logic from before. The stuff in front of the x has to match. So I get to write down the a plus 2b, whatever it is, better be equal to 5. So I guess I'll write it over here. Similarly, this slot is like the number stuff, not in front of any x's, has to match that number slot over there. So I get to write down that -1 equals b minus 3a. Okay, cool. So now I have a system of equations. I have two equations, and I have two variables. That means I'm probably going to be able to solve it, right? Oh, so that was a b. From this system, I have to do some algebra moves to try to solve the system. There's a couple ways to do it. Maybe the easiest way is to just take the first one and solve it for a equals. So I just have to subtract that over. And then I can take whatever I got for a and plug it into the second equation. So I have -1 equals b minus 3a. So I just plug in what I got for a, 5 minus 2b. So I get b minus 15, and then plus 6b. And if I combine the terms, I have 7b minus 15. Or sorry, 7b. I said 7, but I wrote 6. So we have 7b minus 15. And then as our final step, we'll just, remember we had negative 1 over here, so we'll add the 15 over. So negative 1 plus 15 is 14 equals 7b. And so b is 2. So that's the same that we got earlier for b. One thing that's nice about this is that once you have a b, we already know sort of instantly what a is going to be because we have this formula for a in terms of b. So 5 minus 2 times 2, that's a 1. So I know a is 1. So this version will work even if the plugging in numbers doesn't work. So it's good to be able to know. Our steps were starting from here. We multiply out the right-hand side so that it looks like a polynomial. We have number times x plus number, and then we can equate the coefficients on each side and get a system which we can solve. So that's the solving the system version. Okay, so when we do partial fractions, there's always those both ways to do it. Remember, the whole point of this, right, would be to integrate. So this was just algebra, but you know, if we were going to integrate our thing, if someone asked you to integrate this random polynomial fraction thing, I could say, okay, cool, it's the integral of the first one plus the integral of the second one. And those are both ones we can do. Those are u subs. Okay, so I also mentioned something about what the structure of the rational function has to do with what our fraction thing is going to look like. So let's look at this example. So it turns out that if the denominator has, I can factor it into linear factors, distinct linear factors, then what we did above is always going to work. So let's see what I mean by that. We have x plus 2 on the top. Let's just focus on the denominator. X cubed minus 3x squared plus 2x. I want to factor this as much as possible. So first of all, pull out any common terms. So there's an x in everything. So we can do x times x squared minus 3x plus 2. And then I'd like to factor this part. And remember, a good way to factor is to say, okay, what are two numbers that multiply to make this third number, c, and add up to make this second number? So you can think about it, but two numbers that work are x minus 2 and x minus 1. Right? Negative 2 times negative 1 is positive 2, and the negative 2x minus 1x is negative 3x. So when you FOIL, that works. Okay, so that means that our original rational function can be written like x plus 2 over x minus 2, x minus 1. And it turns out whenever it's like this, so I have three linear factors. What makes them linear is it's just x plus something or x minus something. If it was like 2x plus something, that would also be linear. But what's not linear is if you ended up with something like this in your factoring, like an x squared. So we'll see what to do if we have that. But here we have linear factors, and we have three of them. They're distinct, meaning they're all different. Sometimes you'll have like x minus 1 and then another x minus 1 in the bottom. So we'll see what to do in that case too. But if they're distinct, then this will work. And I can write down that this is a over the first factor plus b over the second factor plus c over the third factor. And that decomposition will always work. By the way, I might use this word. This thing on the right is the partial fractions decomposition of the left-hand side. So just like before, we would do some algebra to solve for a, b, and c. I'll just kind of sketch that quickly and let you try that if you'd like to. going to multiply this whole denominator over, right? So the x with the a is going to cancel, and this is all that's going to be left. On the b, we're going to have an x and x minus 1. The other part will cancel. And then on the c, we're going to have an x and an x minus 2. So now you could try plugging in numbers. So I would try x equals 0. You'll get 2 equals a times minus 2 minus 1, and then the rest will be 0. So we'll get a is 1, I think. So I'll let you try kind of completing that, but that kind of logic should work. You should be able to try x equals 1 and x equals 2 to get the other two numbers. Notice here that because of their distinct factors, I can actually pick an x which will get rid of any two of them but keep the third one. That's not always going to happen, but that's kind of why this method works here. Okay, so that's the simplest case and a really common case. And if that makes sense, that's 90%. There are other cases which happen that we should know how they work. And it's going to look a little weird, but there's kind of like a nice table, and I promise it's not that bad. So it turns out, as long as we have a factorization of the denominator, we can look at what the factors are and whether there's powers on them and whether they're repeated or not in order to write down the correct partial fraction decomposition on the right. So this is just kind of like if you could figure this out by carefully writing down a bunch of algebra stuff. Someone figured it out at some point, made a table. So you just kind of have to trust that, yeah, when I add these fractions back up, I really get the original. But it works pretty similarly to the cases we've seen already. So if there's a linear factor in the denominator, which just means, 2x plus 1, something times x plus something, the b could be 0, like 2x is a linear factor. The a could be 1, x counts as a linear factor. Then you're going to get one fraction, which is a over that. Every single factor in the denominator gives you one of those fractions, and then you add them all up. Sometimes you're going to have a factor with a power on it. So like here we have x plus 2 squared. When that happens, the right thing to write down is a sequence of factors. The number of them depends on the k. So like if k is 2, we're going to get 2 factors, or two fractions added up. But if k was 3, we'd get 3 fractions added up. And if k was 10, we'd get 10 fractions added up. What the fractions are generic constants in the top. So here they're writing a1, a2, a3, meaning it's just kind of a list of a bunch of different a's, maybe different a's. And then the denominators are sort of the original one you'd expect, but then getting higher and higher powers as you go. So first to the 1, and then to the 2, and then to the 3, and then to the 4. So it's a little bit weird, but let's see how it works on this example. So here, I know that it's going to be a series of fractions. How many? Well, this denominator is one of these. It's going to give me one fraction. This denominator is one of these, where k is 2. The power is 2. So I'm going to get 2 fractions. So there's going to be 3 fractions total. So I can write a over something plus b over something plus c over something. The first one's going to be your x minus 6. Just copy that. The second one is going to be x plus 2. And then the third one is going to be x plus 2 squared. So this x plus 2 thing sort of generates the list of 2 fractions, one that has x plus 2 to the 1, and then one that has x plus 2 to the 2. And then this guy generates just this one. So again, it's a little bit weird, but if you just do a couple of examples, it'll sort of start to make sense. For example, let's just try, making something up. 32x over x minus 1, x minus 2 cubed, and then maybe x squared plus 1. So we just go factor by factor. So first, the x minus 1, so that's just going to be a over x minus 1. And then you can just use letters as you go, a, b, c. You don't have to do like the a1, a2 thing. So this factor, x minus 2 cubed, is going to generate 3 fractions. The first one is just going to be x minus 2, and then it's going to be x minus 2 squared, and then it's going to be x minus 2 cubed. So because the power is a 3, it generates these 3 fractions where the powers go up as you go. And then there's one more term, this last term. So we haven't talked about this yet. This is a quadratic term. It's not a linear term. So it means it's of this format. So whenever you have something squared, maybe plus something times x, maybe plus a number, that's a quadratic factor. And I'm still going to have that factor itself in the denominator. So I'll have plus something over x squared plus 1. But then it turns out that the right thing to put in the top is a generic linear factor. So I don't know what numbers are going to be here, but there's going to be some number times x plus some number. I'm using E and F because I did D already. So yeah, it's a little bit weird, but that's what works. And if your quadratic factor had like to a power, you do the same like sequence of fractions thing where the powers go up. Something you might wonder about is, do we really only need these two, right? I know how to deal with linear factors and powers of them. I know how to deal with quadratic factors. What if I had like a cube or something? So it turns out you can always factor stuff down to linears and quadratics in a certain sense. And so for most of the time, this is all you actually need. So let's take a look at this example. So this is kind of a doesn't obviously look like it's going to be partial fractions, right? Why do these ones look like partial fractions, right? It looks like partial fractions because it's already been factored in the bottom into some nice linear factors. Once you're familiar with like this table, you can just kind of see that you go from here to here, and there's not really any math to do. But here, it's not like obviously factored yet already. So something we would want to try to do is first factor the bottom. Now the bottom is x to the 4 minus 1. So there's no obvious like things that multiply to the last thing to add to the middle thing, because it's not a quadratic, right? So we have to be a little clever here. You might remember that thing we did earlier, right? The difference of two squares. We said that if you ever have a plus b times a minus b, then when you multiply that out, you get a squared plus b squared. So that's a good algebra thing to have in your pocket, because it means whenever you see something that's something squared minus something squared, I can always factor it using something a plus b and then a minus b, even if it's not like obviously written like this. So for example, like if I did like 9 minus x squared, I know right away that's 3 minus x, 3 plus x. Right? I recognize the 9 as something squared, 3 squared. And so I have the 3 and the x are my a and my b. It could also be like 1 minus y, for example. This is kind of silly. It's already, you're usually happy to see 1 minus y. But I could technically factor this as, right, I need something squared. So 1 squared is 1. So that works. And then I would need y to be something squared. Probably square root of y, right? So this is technically 1 minus square root of y times 1 plus square root of y. So I'll let you double check that if you FOIL that, you really get this back. So that's a really common and useful algebra technique. Here, we have x to the 4 minus 1. So I want to recognize that as a difference of two squares. So it's x squared, right? That's how I get x to the 4. And then 1 squared is 1. So that means I can factor this as x squared plus 1 times x squared minus 1. You can double check if you multiply it out that you really do get that back. So I'm pretty happy about that because now this thing, this whole thing I'm integrating, the denominator is a product of two factors, quadratic factors, which I know how to deal with from the table above. So our original thing we're integrand, I can write as two fractions, right? Something, because I have two different factors. Our table tells us that when it's a quadratic factor, you have to do like ax plus b on the top, and then the factor on the bottom. So here we're going to have ax plus b, and then x squared plus 1. So that's the one that goes with x squared plus 1. And then we'll have cx plus d. So we just need new letters. They can be anything. And x squared minus 1. Okay, so now let's kind of multiply things through to get to that step that we like to get to. So we have ax plus b. If I multiply everything by this, then on this first term here, the x squared plus 1 will cancel, and x squared minus 1 is what's left over. And then here, the x squared minus 1 cancels, and we have x squared plus 1 left over. Okay, this is a good example of it not being super useful to try to just plug in numbers. So I'll let you try that if you're curious, but you will find that if you try plugging in different numbers, the terms aren't going to disappear in the way you want them to, like we did earlier. So instead, we're just going to solve the system. That's going to be our method. We have to multiply everything out on the right-hand side to make it look like a polynomial. So let's see what this looks like. So FOIL this. So we have ax cubed minus ax plus bx squared minus b. And then we'll do the same thing here. So we're going to get plus cx cubed plus cx plus x squared. Sorry, this is dx, right? Cx cubed, and then, oh, that's a cx, and then we'll have dx squared, sorry, dx squared, and then plus d. Okay. So now we can try to match terms, right? So let me just double check something. So back here when we multiplied this through, that cancels, and we have that, and then over here that cancels, and we have that. So okay, so that works. Okay, so let's just collect these terms. So I need to have some stuff times x cubed plus some stuff times x squared plus some stuff times x plus some number stuff. How much x cubed do we got? We got a plus c. We have b plus d x squared. And then how much x do we have? C minus a. And then for number, we have d minus b. Okay. I want to match that with the coefficients on the left-hand side. One thing we haven't mentioned yet here is that, right, like what's b plus d going to match with, do you think? there aren't any x squareds on the left-hand side. But another way I could phrase that is that there are 0 x squareds on the left side. So if I have b plus d x squareds, that better be the same as having 0 x squareds. And so I can write 0 is equal to b plus d. So there's secretly zeros on the left side in front of all the missing ones. How about for cubed? We get 1 in front of the x cubed. There's 1 x cubed. That has to match a plus c. There are again 0 x's, so c minus a is 0. And then d minus b has to add up to -2. Cool, so that's our system. And we just have to rearrange this now. So like I would probably take this one to get a equals c, and this one to get b equals minus d. And now I can plug those into the other two equations. So maybe if we use the first one, 1 equals a plus a, because a is c. So a has to be 1/2. And then maybe from the fourth equation, -2 is, so d is -b minus b. So I have -2 is -2b. So b has to be 1. We know that a and c are equal, so c is also equal to 1/2. And b is minus d, so d is -1. So we get our 4 numbers right away. So it's a little bit tedious, but you can find what those numbers are. We can plug them back into the original, and then that's something we can integrate. So sort of the end result of doing all this is our original integral is the same thing as a x plus b, so 1/2 x plus 1 over x squared plus 1, and then plus, so we can do dx, plus the second integral, which is cx plus d, so 1/2 x minus 1 over x squared minus 1. Cool. So again, maybe that doesn't look like much right away, but this is an easier integral to do than the original. The original is kind of very uncertain looking, but here we have some progress we can make, right? I do have to split it up a bit more if I want to get the final answer. So let's see. Remember, I can split the fraction, and I can pull the 1/2 out. So I'm going to have like 1/2 this guy. And I can split the fraction into 2 different integrals, right? So this first integral splits into these two, plus. And then the second integral splits into these two. So there's still quite a bit of work to do here, and so that's okay. But we had to use partial fractions to even get here. Most partial fractions problems will be a little bit shorter than this. I just kind of want to show a long one. I'll let you try to finish this integral. Some hints. So try it, and if you want some hints, here's some hints. So this is a u sub. This is also a u sub. And this will be a arctan.